So you have heard everything about me, so I really do not have to introduce myself now. I'm here to talk about this 1 billion social network, but this is not the only reason why I'm here. I have recently heard that there are many people who say Scala is not suitable language for commercial solutions, and I would like to give you an implicit evidence that this is not true. So my previous experience with things I thought is big data was about 10 millions of documents in a relational database, about 60 millions of documents in a document database, and about 60 million vertices in a graph, and that last one was not a commercial experience. And the social network can be represented as a graph. This is true, and once upon a time, our former client came to us and told that they have a second project. We didn't know that project yet, and that project was in production, customers were using it, but they had serious problems with data consistency, bugs, and availability, and so on, so they required our help. And so we have assigned 4 software engineers to help in this project. That graph, as a social network, consisted 2 types of vertices. First one, the company vertex, and the second one, the user vertex. Those vertices were connected with 2 types of relations. The first one worked between companies and users, and the second one, the second type, knows between user vertices. The idea of that application was to provide to the end user the subset of the graph. And to provide that subset, we had to do the graph traversal. So let's assume we are from the Foo Incorporated, and as a customer, we want our subset. So we start from the Foo Incorporated vertex, we go through work relations, and then we go through nose relations, and we got our subset. Easy, and quite short path. And after digging into the code, we have realized that we've been tricked a little. That graph was not a billion challenge. It was 830 million vertices challenge. And we were a little bit disappointed because $1 billion sounds like $1 million, but it's quite big enough to have fun with it. So those subsets I've talked about, I cannot see that, were about varied from thousands to millions of users. So the smallest subsets for the end user were about 2,000 to 3,000. The biggest ones, 3-4 millions. We were excited. We wanted to do that project, so we tried hard. And what we have seen cannot be unseen. The existing application stored all profiles in Amazon Redshift, about 750 million profiles and much more data. And when a new customer came to the company, he called success team, and success team filled the ticket. And in the evening, the software engineer opened the ticket and ran manual scripts and extracted data from the Redshift to JSON files. And then he loaded those profiles into MongoDB. And on this stage, there was data duplication, because for each customer, for each client, they duplicated profiles. And then from here, he loaded those data into Elasticsearch. So when we were working on this project, in the Elasticsearch was about 60 million of documents, including duplicates. And this whole process took about 1 evening engineer. We didn't know what is that, but this is what we have heard. And from the perspective of the client, of the end user, it was a few days at least. So for us, it was unacceptable, and we had to prepare something better. So we have decided to prepare POC. Why POC? Because we had not enough experience, and we didn't want to tell client, this is bad, and throw it out. We wanted to give him something better and tell, we can do this like it should be done. Our goal was to handle this whole 1 billion graph, 1 billion network automatically. Simple as that. And the definition of done of this POC was to prepare the REST API that serves search endpoint, and which allows a graph traversal, and which allows full text search and filtering and sorting in the near real time. So we wanted to have a graph traversal on demand, and first results available under first minute when the client comes, and the whole subset in few minutes. So what was the concept for our application? It was quite simple because it's a POC. We wanted to build API application, use graph database for all relations, and use document database for all profiles. Why graph database? Why not Redshift again? Because graph database allows us to fast graph traversal. It's easily extendable with new relations, new types, new data, and the description of the algorithm, of the core of the idea, is very convenient. So what will be the flow here in this POC? Oh, it didn't work, sorry. What will be the flow in this POC? It will be to generate the subset inside of graph database, where all relations and all vertices are. And then to tag documents, existing documents, in DocumentDB. So with unique ID, we tag documents and then can filter them out when user is searching. So what was the weapon of choice? Quite easy, Scala and Play framework for API. And we had to decide what to do with graph database and document database. To decide, the first step was to extract data from Amazon Redshift. We have extracted anonymized data, and it took a few days. Amazon Redshift was so slow. We were just streaming with Akka and Slick records one by one. Then we had to push those data forward into the document database and the graph database. And we didn't know at this stage what tools we would use because it would depend on the choice. So for the full-text searchable document database, it was quite easy. We have before used Elasticsearch, and it's quite a mature solution. It's very scalable, horizontally scalable. It allows us fast indexing, and it's quite well documented. The documentation is exhaustive. And also, it's really convenient to use in Scala because of Elastic4S library, which wraps the original Java library. And because of Play Elastic4S library, we have built in Evojam, which provides implicit conversions to JSON to play JSON classes. So, which graph database to use? This was much harder because we had no big experience. We have considered TitanDB, OrientDB, and Neo4j. And what I have started with was Titan, because Titan looks cool. It's built on top of Cassandra. It's built on top of Elasticsearch, and it works well. I have loaded a 60 million vertices graph into Titan, and it was great. It was worked fast and reliable. And I have saw that on GitHub that Titan is probably not no longer maintained. I don't know, maybe it's on hold or it's abandoned, but I don't care. I cannot recommend that to my client. So we have left Titan, and then we have tried OrientDB. Last year, on the previous Scala, I have heard about OrientDB, and I wanted to give it a try. Loading data into OrientDB was quite slow, but it performed stable. Stable until about 200 or 300 millions of vertices and relations, because after that, OrientDB refused to work further. It was accepting new queries, but not even parsing them. I could query and read data, but not put more data into OrientDB. And again, I didn't want to debug it. I didn't want to fix existing solution. I wanted something that works. So the only left was Neo4j, the one I have experienced. I had experienced before. Neo4j is quite cool because it has a batch insertion, which does not have OrientDB. And this tool is provided bundled with the Neo4j. So also the advantage is the library for Scala, which uses REST API from Neo4j, which is not very fast, but reliable and works. And this API also has a streaming capability of results. So for our usage, it's perfect. So when we decided what we would use, we had to deploy that, and we were deploying on AWS. So the setup of AWS for this application was to use a single instance for API, only 2 CPUs and 8 GB of RAM. Quite big machine for Neo4j, 8 vCPUs and 60 GB of RAM. And for Elasticsearch, 2 instances, both 4 vCPUs and 30 GB of RAM. As I told you, bulk loading into Neo4j was easy because of the bundled tool, And it took about 3.5 hours to import all 830 million of nodes and almost 7 billion of relationships. And I have tested this tool on the machine twice times smaller, and it took 12 hours. So it scales well, it uses all the resources it can. The next step was to load data into Elasticsearch, and here we had no tool for that. So we have built one with Akka and Akka Streams. And why Akka Streams? You can read CSV file line by line, but we had to generate more data, like data from the CSV file was anonymized, only IDs and not original one. So you had to add some full-text searchable data. And to parallelize that, we used Akka Streams. It's quite easy to do that with Akka. The first stage was to generate in parallel those data. The second one, to group profiles into chunks and then push into the bulk requests to Elasticsearch. So this is the code that describes this process, and I believe it's readable. It's human readable so easily that I love Akka Streams, because after a year or two, I will understand what's happening here. The next step was tagging. And again, we wanted to generate the subset in the Neo4j and then tag existing documents in the Elasticsearch cluster. So just to recap, this is the subset, which may be from few thousands to few millions. In Neo4j, it's quite convenient to describe such a subset. And this is the query in Neo4j that allows us to fetch those data. So we match for company, then through work relations to employees, and then through nose relations to acquaintances, where the ID of the first company is which we want, but we do not want those users who worked already in that company. And we return distinct set. And again, Akka Streams came to the rescue. This implementation of Neo4j client returns a numeric T from Play Framework, which is not very convenient to use. I didn't like it. But thankfully, we could convert this easily to the Akka Stream. And when I have first time run it, this had never ended. And I said, hello, what's happening here? The problem is that there's a bug in the underlying implementation, and I had to add a simple additional stage, this one, which is implemented in few lines, in fact, which buffers those data from Neo4j, and when the stream stops flowing, it times out. And again, it's readable, it's easy, and it's convenient. So, this is the simple approach. We are tagging profiles one by one, with rate about 670 per second. For that sample with 3 million of users, it would take about an hour and a half. Oh, sorry, it's too long. We have indexing latency constant, we have constant speed, but it's too long for our end user. So we made simple change in our stream. We have introduced grouping and execute bulk indexing in Elasticsearch, and our indexing rate has grown to 6,000 per second, almost 6,000. So for a sample full company, which has about 2,200,000 profiles, we have 14 seconds until the first batch is tagged. It's quite cool. It's almost as fast as I would like to have. And remember that machine for API was quite small. We have 7 minutes until whole subset is tagged and available for searching. So the end user can search for these profiles in database after 14 seconds, and after 7 minutes, he has whole results ready. For the reference implementation took about a few hours at least, and it was not automatical, so a few days. So the next step was to search in that data set, and as you remember, we wanted to have a full text search. So the sample request was to search in the company with random phrases. And recap, we are searching in 2 million subset. So we are using 2,000 phrases, random phrases, for benchmarking. And majority of those phrases were in this subset. We were using Siege with 50 threads benchmarking. And the API was returning 50 profiles in result. So, and whole database is about 750 millions, not 60 millions like a reference implementation. So under the Siege, we had about 140 milliseconds of average response time. And inside of Elasticsearch, it was quite OK because the search rate was stable and was about 737 per second searches. And latency was also constant. So I believe our objective has been achieved. We had 14 seconds until the first batch was tagged, and we had about 7 minutes until 2 million of documents were ready for searching. We had search response time from API on average about 140 milliseconds. So in a month, we have implemented the working solution that was much better than the reference one. A short comparison, and majority of them I have just told you, but the last one is not visible for you, sorry, but it's quite important. We know that graph traversal is a core idea of the application, but it may change. But to change the graph traversal algorithm, someone has to work on that graph. And a reference implementation from Redshift was not able to give a data scientist, data analyst access for researching. And on our Neo4j, one could run graphics, because it's graphics ready through Maze Runner. So someone who wants to go through and search for better patterns can easily work on it. So just a short summary. We have used Scala, Play Framework, Akka, Neo4j, and Elasticsearch. And it's quite tough to find such data set for yourself if you would like to work with it at home. Quite good examples are available on Snap project from Stanford. There are several graphs, real life examples that you can use, you can download, use for your research. So, I would like to encourage you, because Scala and all those tools are perfect for solving such solutions. And you can do that at your home. You can learn how to tackle a graph and then use it in your everyday commercial project. So thank you. If you have any questions, we have time now, so please ask. I guess there are no questions. So thank you very much for listening.